So now we have modeling techniques, and we're not going to cover all of them today. And really, when we're talking about this, I just wanted to include a bunch of information as far as different ways that modeling is done. And this is mostly from a reference perspective, because a lot of the stuff that you guys will be asked for actual modeling is kind of stuff you guys have already experienced in real life. There are some sort of things I'm going to have to calculate here from a little bit of a modeling perspective, but well, let's get to it. So simulation. There's different things you can simulate. You can simulate using different things. And with that, basically what you're doing is trying to imitate some sort of real-world process or some sort of real-world system over X amount of time. You're going to have iterations. You might do simulation multiple times. There's going to be your outputs. You're going to have to study, and if you're going to see if it actually represents, that real world process or system, and if it also represents your expected results. If it doesn't, then you might have to do a redesign, right? Redesign your system, or look at your actual model to make sure that you have the right inputs. Of course, they use simulation in many contexts. We see simulation all the time when we see, people learning how to fly a plane, right? You could be in the cockpit and then pretend you're flying, and people learn that way, and then they go out there in the field and really do it based off what they learned in the simulation. All different types of things. SolidWorks, we could do simulation there. Modern Sim, the group that I work closely with right now, they do a lot of Modern Sim for a projectile, a missile that flies in the air. They do Modern Sim for all different types of things out there. Okay, now you have continuous simulation, you have discrete event simulation. For continuous simulation, you have a model, a physical system. It just continuously tracks the system response according to some sort of set parameters involving differential equations. For your discrete event simulation, it's going to be some sort of discrete sequence in time. So, you could say, let's model this thing as it's heated from 50 to 70 degrees Fahrenheit, and will fluctuate within here. Well, we know it's eventually going to go to 120, so now let's do from 71 to 90, and then we do 91 to, those are more of the discrete event simulations where you're kind of looking at these, start-stop points at a certain instant in time, and seeing how the system reacts as you are basically looking at that model. Here, it states that the simulation can directly jump in time from one event to the next. And again, that's just because it's discrete and you have your setup already. I could do from 50 to 70, 71 to 90, etc. We have these random number generators, which, a lot of us have used, Monte Carlo simulations, which, extract information from these random number generators. Essentially, this simulation generates random variables of all different types and depends on the system model itself. You could use different pseudo-random number generators. All these number generators are just some sort of algorithm that uses mathematical formulas to produce random numbers, right? That's all it is. So there's different types of different types of random number generators. Here we have the inverse transform technique, which is in the reference handbook. We have direct transformation, convolution method, and acceptance and rejection techniques. The inverse transform method, basically you're going to get a number that's going to be generated from some sort of uniform distribution that's in some sort of interval, right? So from 0 to 1, and this is my distribution, and these are all the numbers we can get between this. Again, no need to really go into detail about this, but I just wanted to tell you that there's different ways that you could generate numbers.